All right, so example 19 is asking us to prove by the principle of mathematical induction that the following is true. So this on the left, we have the sum of the first n counting numbers, and we're asked to prove that this is equal to n into n plus 1 over 2. So let's start by writing down the statement that we're being asked to prove. We're being asked to prove that the sum of the first n counted numbers, represented in sigma notation like this, are, which is 1 plus 2 plus 3 plus 4 all the way to n. So this would be equal to n into n plus 1 all over 2. That's what we're asked to prove. So 1 plus 2 plus 3 plus 4, adding the counting numbers all the way to n, is represented by that in sigma notation. All right, now the first thing we need to prove is that the statement is true when n is equal to 1. So when n is equal to 1, P1 is asking us to sum the first counting number. Well, if you're adding the first counting number, which is 1, you're not adding it to anything, so it's just 1. So this is the left-hand side. And on the right-hand side, when n is 1, we have 1 into 1 plus 1 all over 2, right-hand side. So this is 1 times 2 over 2, which is 2 over 2, which is equal to 1. So when n is equal to 1, both the left-hand side and the right-hand side are equal to 1. So we can say that Pn, which is the statement that the sum of the first n counting numbers is equal to n into n plus 1, is true, n plus 1 over 2, when n is equal to 1. So this is step 1. Step 2, we're going to assume that Pk, which is the sum of the first k counting numbers from 1 to k of r, which is 1 plus 2 plus 3 plus 4 plus k is equal to k into k plus 1 all over 2. We're going to assume that this statement is true. Then 3, we are required to prove that Pk plus 1, which is the sum of the first k plus 1 counting numbers from 1 to k plus 1 of r, which is 1 plus 2 plus 3 plus 4 plus k plus 1 is equal to, wherever I see n, I'm going to put k plus 1. So this is k plus 1 multiplied by k plus 1 all over 2. Simplify, we get k plus 1 multiplied by k plus 2 all over 2. So that's what we're required to prove. We're required to prove that the sum of the first k plus 1 counting numbers is equal to k plus 1 times k plus 2 over 2. So using the left-hand side, which essentially is saying from r is equal to 1 to k plus 1 of r, which is 1 plus 2 plus 3, up to k, then to what? K plus 1. So that's the sum of the first k plus 1 counted numbers. But the sum of the first k counted numbers, according to step 2, is equal to k into k plus 1 over 2. So this is k into k plus 1 over 2 plus the k plus the last counted number, which is k plus 1. And let's put this over 1. We're going to make this into one fraction. If we're adding or subtracting fractions and the denominators are different, we must find the LCM. So our job is to prove that the left-hand side is equal to the right-hand side that we have over here. The LCM is 2. So we're working the left-hand side now. 2 into 2 is 1. 1 times the numerator, we get k into k plus 1. 1 into 2 is 2. 2 times the numerator, k plus 1. Now, looking at the numerator, we can see that k plus 1 is common. If you factor out a k plus 1, now k plus 1 into k times k plus 1 is k, plus k plus 1 into 2 times k plus 1 is 2, and this is all over 2. So this is the left-hand side. And at this moment, you can see that this is equal to the what? Right-hand side. So now that you have done this now that 3 is complete, once 3 is complete, step 4 is to make a statement. And the statement is this, that k plus 1, which is the sum of the first k plus 1 counted number, is true when pk is true. Therefore, Pn, which is the statement, the sum of the first n counted numbers, is equal to n into n plus 1 over 2, is true for all n, which is an element of the set of natural numbers. So largely that last statement is the same all the time. All right, so the next example we're going to look at, remember we did example 20 already. So the next example we're going to look at is example 21. So example 21 is asking us to use mathematical induction to show that the following formula is true for all natural numbers. All right, I'm going to try and spell this out for you. So I'm going to try and make this, I'm going to expand the series a little. So Pn is the statement from r is equal to 1 to n of 1 over 3r minus 1, 3r minus 2 over 3r plus 1. So if I expand this series, I'm going to say when r is 1, this becomes 1 over 3 ones are 3 minus 1, you get 1. Multiply by 3 ones are 3 plus 1, you get 4. That's the first term. That's when r is 1. When r is 2, you get 1 over 3 2's 6 minus 2, you get 4. Multiply by 3 2's 6 plus 1, you get what? 7. If you're observant, you'll notice that both the first term and the second term is increasing by 3. So the next term would be 1 over 7 times 10. We can't write all of them. And we're going to continue doing this until the nth term, which is 1 over 3n minus 2 multiplied by 3n plus 1. And this we're told is equal to n over 3n plus 1. We need to prove that this formula is true using induction. So the first step, as usual, is show that the statement is true when n is equal to 1. We have P1, which we already worked out already. When r is 1, on the left-hand side, we have 1 over 3 times 1 minus 2. 3 times 1 plus 1. This is the left-hand side. On the right-hand side, when n is 1, we get what? 1 over 3 times 1 plus 1, right-hand side. Over the left, this works out to be 1 over 1 times 4. On the right, it works out to be 1 over 4, which is essentially just the same as saying 4, which is the same as saying 1 over 1 times 4. So when n is 1, both the left-hand side and the right-hand side are equal. So we can say that Pn is true when n is equal to 1. That's step 1. Step 2, we're going to assume that Pk, which is the sum of the series from r is equal to 1 to k, Pk, which is from r is equal to 1 to k of 1 over 3r minus 2, 3r plus 1 is equal to k over 3k plus 1. We're going to assume that this statement is true. Then we are required to prove that pk plus 1, which is the sum of the same series, from r is equal to 1 to k plus 1 of 1 over 3r minus 2 multiplied by 3r plus 1 is equal to, over to the right, wherever I see n, I'm going to put k plus 1. So it's k plus 1 over 3k plus 1 plus 1. Simplify to k plus 1 over 3k plus 4. That's what it simplifies to. So this is what we're required to prove. This is our step 3. Once we prove step 3, we're basically finished. To prove step 3, we're going to take the left side. But what you must remember, that with a series, the sum from r is equal to 1 to r is equal to k plus 1 is actually the what? The sum from when r is equal to 1 to k plus the k plus 1 term. So p k plus 1, which is the sum of this series from r is equal to 1 to r is equal to k plus 1, is actually equal to pk plus the k plus 1 term. So you're going to sum, but pk from step 2, which is step 2 here, is equal to k over 3k plus 1. From step 2, that's what pk is equal to. Plus now the k plus 1 term. The k plus 1 term is when r is equal to k plus 1. From the general term, when r is equal to k plus 1, we get 1 over what? 3 times k plus 1 minus 2 multiply 3 k plus 1 plus 1. Remember, we're working the left-hand side. This is k over 3k plus 1 plus 1 over 3k plus 3 minus 2. This is 3k plus 1 multiplied by 3k plus 3 plus 1, which is 3k plus 4. We're still working the left-hand side, and our objective is to get it to look like that. That's our objective. Once we get the left side to be that, we're finished. All right, well, we're going to add the two fractions. The LCM is what? 3k plus 1 multiplied by 3k plus 4. I don't want anybody to get nervous over that. This is like somebody's asking you to add k over a plus 1 over ab. The LCM would be ab. So it's the same pattern. The LCM for these two fractions is, for the LCM of the denominator is k plus 1 multiplied by k plus 4. That's the LCM. Now, k plus 1 into k plus 1 multiplied by k plus 4 is, into 3k plus 1 multiplied by 3k plus 4 is 3k plus 4. This is all I just said. 3k plus 1, 3k plus 4, divide by 3k plus 1. That cancels that, leaves 3k plus 4. I'm going to multiply the 3k plus 4 now by the numerator, which is k. So it's k times 3k plus 4. Plus 3k plus 1 multiplied by 3k plus 4 into 3k plus 1 multiplied by 3k plus 4 is 1. Everything goes into itself one time. 1 times 1 is 1. So I'm adding the two fractions, making them into one fraction. So we have what? 3k plus 1 times 3k plus 4. All right, up top, let's remove the bracket. Remove the bracket, we're going to get what? 3k squared plus 4k plus 1. The next is to factorize the numerator. I'm factorizing by trial and error. Now, how do I go about doing this? I'll try and give you some insight. Whatever I put here and here, when I multiply them together, I must get what? 3k squared. Now, the only two things you can multiply together to get 3k squared is k and 3k. The only thing that can go here is 1. The only thing that can go here is 1 and 1. Whatever I put at the end of both brackets, when I multiply 1 and 1, I'm going to get back what? 1. Since everything is plus, it must be this. I just factorize the expression. And this is over 3k plus 1 multiplied by 3k plus 4. Now, if you look carefully, you'll notice that these two are common, so I can cancel them. When I cancel them, I'm left with what? K plus 1 over 3k plus 4. This can't be simplified any further, so now let me check if this looks like what I have over here. And you can see it's the same thing. I just got the left side to become the right side. And once you have done that, you can now make your statement that pk plus 1 is true when pk is true. Therefore, Pn, which is the statement from r is equal to 1 to n of 1 over 3r minus 2, 3r plus 1 is equal to k over 3k plus 1. I think that's what it should be. Sorry, it's n actually, it should be n. N over 3n plus 1. Is equal to n over 3n plus 1 is true for all n, which is an element of the set of natural numbers. All right, so let's just scan back to it very quickly. And this is what we're asked to prove. These are the steps, the 4 steps that you have to take to prove the statement using the principle of mathematical induction.